3, 2, 1, go. And we're live. This is Retraice segment number 106 for Wednesday, January 4th, 2023, 10 p.m. Eastern, 7 p.m. Pacific. Retraice is about what's going on out there. The short answer to that is computer control, by which we kind of mean what you probably mean when you think of AI, but it's way bigger than that. Long answer to that has come in fits and starts and waves that you should go review in the archives. Okay, so what are we talking about? We are in day 4, chapter 4 of our deep dive, AIMA4e, Artificial Intelligence, a Modern Approach, the textbook 101 AI textbook for AI, and local search and optimism. No, it's a search in complex environments is the title for chapter 4. I just, things are getting interesting. I keep saying that. I said it last time. I'm going to keep saying it. If things continue to keep getting, we're on, what, in the 120s, 140s, whatever. If things continue to get more interesting than the day before, things are going to be crazy interesting in about 3 weeks. Okay. A few technical terms have come up that, as I said in the title, and as you would have noticed, maybe that's the clickbaity reason that you're watching this video. If you are watching this video and you're expecting me to talk about the imprecise English language meanings of those words, okay, I might do that a little bit. No, I'm not going to do it that much because the thing that makes it interesting to us right now is the technical definitions. The technical definitions of elitism, culling, coercion, adversaries, and strategy, which all come in chapter 4. But like the technical definitions always derive, I find, in technical things to the extent that I have experience with them, which is to say, a little bit. They derive from the real meanings. There's a lot of baggage is stripped away, and that baggage is what makes a term so loaded. So let's unload it, and then really load it into AI. All right, what are we talking about here? So elitism and culling in evolutionary algorithms is what we're talking about first. I'll just read the passage that caught my eye as these things, one of them. There are endless forms of evolutionary algorithms, and they vary in the following ways, and then they give a list: population size, representation of the individual, mixing numbers, the number of parents, the selection process, all this technical stuff that you can tweak and fiddle with if you're doing evolutionary algorithms. But then the last one gets kind of, gets a little bit too close to home. Not for me, but like for our civilization, I would say. Okay, the makeup of the next generation is another thing that can vary in genetic or in evolutionary algorithms. This can be just the newly formed offspring, or it can include a few top-scoring parents from the previous generation, a practice called elitism, which guarantees that overall fitness will never decrease over time. So they're saying the next generation can either be all new, no parents, or there can be parents above a certain threshold of fitness, and they call that elitism, the latter thing they call elitism. And then the practice of culling, in which all individuals below a certain threshold are discarded, can lead to a speed up of the evolutionary algorithm. Okay? So these are not red hot. These are third rail. What are these? These are electrified, overheated ideas. It's like social Darwinism, all this stuff. This is like part of the origins of Nazism, and the Nazis definitely jumped on board with it. I don't know the history of Nazism that well, but yeah, like if Darwin's right about, we're better, we are more fit than gorillas, well, maybe some of these humans are more like gorillas than I am, right? Right? Ugh. Don't start thinking that way. And yet, when we're doing evolutionary algorithms, which I'm not sure is wildly successful for engineering purposes, as people had hoped. Although I think they mentioned using them to make airfoils, to design airfoils. When we put it in the technical world of artificial intelligence, computer science and artificial intelligence, yeah, why not? I don't care if this population of strings or programs, that's genetic programming. I don't care if this population feels like it's fair for me to call them or kill all their parents, but that's what you're doing with it. You're not fit enough. And this generation is too unfit. We're going to keep some of the parents around so the gene pool stays elite. It's like I'm being tongue in cheek. This is like this is the stuff of nightmares. So this is a recipe for nightmares and hell on earth if you start thinking this way about your fellow humans. So don't. But I don't have to tell you that. If you're the type of person who would think that way, you're not going to stop just because someone tells you. But hang on a second, like, and evolution is like this more generally. If you read The Selfish Gene, Richard Dawkins, you'll get, I feel like you come away with two things. First of all, it's way more complicated than it seems, evolution. Like you can't just armchair it. And there's somebody, I don't remember who said it, but the strange thing about the theory of evolution is that everybody thinks they understand it. It's very logical and mathematical, more logical than mathematical, but math is easily applied to the theory of evolution. But the logic is hard, and it's very easy to think, oh yeah, I know what would happen because of evolution, and then it's like you don't. And like the professional biologists make mistakes all the time, and Dawkins catalogs them in The Selfish Gene and in the updates to that book and all that stuff. Anyway, evolution is a tough topic, but what you can be sure about also is that it's a harsh world described by evolution, very harsh. But biologists, they love their subject, and they don't really. Nobody gets really upset about the doom of a stupid animal, or a slow animal, or an animal with some genetic, mutation. Nobody cares, right? Because we don't care that much about animals. Like only a few people do. We care about humans, right? Because there's only so much care to go around. We can't go around care. And this is our whole environmental problem. Why am I getting into this? I don't want to write all this up. Anyway. The point is, they're doing that in AI. They're taking just the logical idea of evolution and its parameters and fiddling with them, trying to do something productive. And of course they should be doing that. Biologists are doing the same thing. Not chemical engineers, bioengineers. Are bioengineers? They're not allowed to do a lot of stuff. But anyway, I don't know any bioengineers. If you're a bioengineer, write to me. Tell me what I should think about you. This is maybe the more general theme of this segment. No, I'll get to that later. Okay, so that's the first hot buttons topic. It's like evolution is not a nice thing if you're on the wrong side of it. Okay, coercion in sensorless problems, conformant problems. I wanted to say sensorless environments or sensorless search, but I think the problems is the most technical word I can put on it. I don't see justification for saying sensorless search or anyway. So here's what they say on page 126. Consider a sensorless version of the deterministic vacuum world. They use the vacuum world to elucidate all kinds of search stuff, almost all of it, because it's a really useful toy problem, really useful. Maybe more useful than, or at least as useful as Romania. No offense, Romania. Like, I'm sure you're good for a lot of things, but it just so happens that your layout and your need for transportation insights and airport construction is very useful to us in AI. Look at me, us, like I'm part of it. Okay, anyway. So they use vacuum worlds, different sort of situations that an automated vacuum, an AI-based vacuum could be in, and then the kind of vacuum. Okay, so anyway, in a deterministic, sensorless vacuum world, assume that the agent knows the geography of its world, but not its own location or the distribution of dirt. In that case, its initial belief state is 1, 2, 3, 4, 5, 6, 7, 8. Okay, belief state is just a list of states that you believe you might be in. If you're in a sensorless world you don't know, and it's an unknown world to boot. So you instead of being in state 1, which is when you're in a known environment, you have to adjust how you think and what you supply to your algorithms. If you're in an unknown world, or as an example, the sensorless world. Okay, so our agent here, our vacuum agent, believes that it could be in any of the, and then there are only 8 states in this toy problem. Okay, so any of your belief state is 1, 2, 3, 4, 5, 6, 7, 8. Now, if the agent moves right, it will be in one of. Okay, so I should actually pull up, if I can, figure, what is it, 4.9? Okay, fine, 4.9. I knew I was going to use a different one, but show me, no, that's not it. No, not 14.9. Oh, jeez. There we go. No. Here, 1, 2, 3, 4, 5, 7, 8. These are the states that our little sensorless vacuum can be in, okay? If you believe, whoops, what am I doing? Oh, yeah, okay. Okay, so now if the agent moves right, it will be in one of the states 2, 4, 6, and 8. Let's have a look, okay? So it starts out in 1, and it moves to the right. So any of these over here, 2, 4, 6, 8, it moves. And this, I think this assumes, too, that the agent it's a deterministic environment, which means basically in our toy problem, it means the vacuum doesn't slip. Like, it doesn't try to move right and then fail to do so. It's not slippery. It's not a slippery world. So if it executes the action move right, it starts out in state 1, then it definitely ends up in state 2, 4, 6, or 8. Okay, great. The agent. Okay, so now if the agent moves right, it will be in one of the states 2, 4, 6, 8. The agent has gained information without perceiving anything. That's what's wild about it. That this is a sensorless vacuum, and it knows the geography, so it knows there are 8 states, but it doesn't. And I don't remember if it knows it's sensorless, so it knows which squares have dirt in them, because I think that's considered part of the geography. I don't know. And so then so the next one is after right and then suck, which is what the vacuum does, if you're not aware. Okay, so it moves right, and then it sucks up the dirt. And now, what do we know? We know that it's either in 4 or 8. Okay? So we're sort of narrowing this down. Is that what they say? Let's make sure I got this right. Right suck, the agent will end up, 4 or 8. And finally, after right suck, left suck, I know I don't want to keep saying it that way either, but they do it throughout the whole first few chapters. So it's in 4 or 8, and then it moves left, and it sucks up some dirt. Then it can only be in state 7. Show me 7. Did I do it right? It can only be in the goal state of 7. No matter what the start state, we say that the agent can coerce the world into state 7. And actually, I said it wrong. I guess you don't have to start in state 1. If you start in 2, 4, 6, or 8 and you move right, then you'll still be in 2, 4, 6, or 8, because when you move right into a wall, you just stay where you are. If you start in 1, 3, 5, or 7, you move right, you'll end up in these. So even you don't have to start in state 1. The point is we're coercing the environment. Have I said that point? We're coercing the environment without even paying attention to it. Only by knowing its geography have we been able to coerce the environment into the goal state. Now, if you weren't sure about the power of AI, now this might not seem like AI to you, but that's what's even more important about it. This is very basic stuff. This is just think it through sort of stuff. Now, everything in math and AI and computing is like that, but it's like think it through there's think it through, and then there's 2,700 steps in human history that were involved in the think it through. This is not one of those. The idea that's so noticeable, that's so salient, is that you can coerce an environment. If you know the environment to start with, you don't have to know where you are. You don't have to know what's going on. Now, this is offline search because we're not in some sort of loop with the environment where you have to consider perception of the environment, and online search we can plan the whole thing. Offline search we plan the whole thing in advance. Online search, and it's like we're sort of in a more realistic loop, a feedback loop with the environment. But anyway, coercion. Have you ever felt coerced? Have you ever worried about being coerced? If you listen to this podcast, you should. There's some paranoia in this podcast. Paranoia is fun. Life is more interesting. If you're not paranoid sometimes, you're missing out. It's fun to think about this stuff. So anyway, vacuums might be coercing us into their goal state. Next topic. Adversaries. These aren't all in pagination order, in case you hadn't noticed. Adversaries and dead ends in online search. This is from page 136. Online explorers are vulnerable to dead ends. Oh, I got to show you a graphic. I'll show you a graphic in a second. Online explorers are vulnerable to Online, again, means you're in a feedback loop with the environment, so you're not planning all your actions in advance. You're actually making decisions based on the percepts you receive in the environment during execution. Okay, online explorers are vulnerable to dead ends, states from which no goal state is reachable. If the agent doesn't know what each action does, it might execute the jump into bottomless pit action and thus never reach the goal. In general, no algorithm can avoid dead ends in all state spaces. Consider the two dead-end state spaces in Figure 420A. Let's consider those two dead-end state spaces. 420, again. I must be near it. There it is. So I'll just read the caption here. Two state spaces, we're just talking about A right now. So two state spaces that might lead an online search agent into a dead end. Any given agent will fail in at least one of these spaces because you can't, if you don't know the environment, you start at S, you go to A, and then you make a move to an unknown thing, and then you make one more move, and then you're at a dead end. You can't tell the difference based on that series of steps, whether you're in the dead end or in the goal state, unless you test for the goal state. But the point is, these things look the same to an online agent, going this way to a dead end and going this way to a dead end. Okay? Okay, so that's 420. An online search algorithm that has visited states S and A cannot tell if it is in the top state or the bottom one. Yeah, the S and A. I guess you can't tell which one you're at here. I went a bit too far by saying that you get all the way to the dead end, because if you're testing for a goal state, you're going to know you're not in the dead end. But anyway, okay. Therefore, there's no way it could know how. Hang on. Cannot tell if it's in the top state or the bottom one. The two look identical based on what the agent has seen. Therefore, there is no way it could know how to choose the correct action in both state spaces. This is an example of an adversary argument. We can imagine an adversary constructing the state space while the agent explores it and putting the goals and dead ends wherever it chooses, as in Figure 420b. And here they describe this as a two-dimensional environment that can cause an online search agent to follow an arbitrarily inefficient route to the goal. Whichever choice the agent makes, the adversary blocks that route with another log, with another long, thin, it might be a log. No, it's a long, thin wall. With another long, thin wall so that the path followed is much longer than the best possible path. Okay? So, adversaries, not this guy is my enemy, or these people are working at opposite purposes. Technical adversarial argument we're talking about here. We're taking these squishy English words and not stripping them of their common sense meaning, just making their common sense meaning more technical, or making a technical meaning out of their common. And what does it mean? When you make things technical, you're making technology, tools for dealing with this stuff. I'm going to tell you why I care about this, or why this excited me in a second. Okay, that's adversaries and dead ends. Strategy in partially observable and non-deterministic environments. That's what this whole chapter is about, by the way. It's like the more complex search and what's the third one? It's not, anyway, it doesn't matter. Okay. In partially observable non-deterministic environments, the solution to a problem is no longer a sequence, but rather a conditional plan, sometimes called a contingency plan or strategy, that specifies what to do depending on what percepts agent receives. And that's, I think it's a typo. The agent. I think it should be the agent. On what percepts the agent receives while executing the plan. Okay, so strategy. Friedman, where is he? He's not up here. He's in the basement. I don't even remember his first name. Friedman wrote a book called Strategy. He's the same guy who co-wrote the nuclear strategy book. He spends this many sideways. This thing is like, it's like 1,200 pages, trying to define strategy. And I've seen other people try to do it too. They didn't take that many pages. It's a good book, but he doesn't define strategy. They did. It's a conditional plan in a partially observable or non-deterministic or both environment. Conditional plan that specifies what to do depending on what percepts the agent receives while executing the plan. That might not seem very useful to you when you're having a conversation with someone about strategy, or when you're trying to get a job as a strategist, or you're trying to comment or commentate on someone else's strategy, but it is a very technically useful way of using that word. These ideas, and this chapter in particular, and I'm starting to get into the parts of the book that I have not read thoroughly. Like I think up to page like 120, maybe, yeah, something like that. Maybe less, like 110. I had read like last year, like Q4 of last year. I read pretty carefully. But now we're getting into chapter 4, which I've only dipped throughout the rest of the book. I haven't read anything very thoroughly from here going forward. So this is the first time I've read this stuff. It's the first time I've ever thought, oh, that's the answer. And that's the answer to what? Major Murphy. Jacques Vallée's Major Murphy Messengers of Deception problem. This Major Murphy's not the guy's name, but it's a pseudonym Vallee uses for some guy in military intelligence or, in the military. It's to do with UFOs and what is it all about and all that stuff. And that Major Murphy makes the point that like scientists can't investigate these things. If we're dealing with intelligent agents, science will fail because science assumes things like the constancy of nature, and it assumes that a natural phenomenon is not trying to evade it. That's what this is about. That's exactly and what's the answer? If science isn't the answer, what's the answer? Artificial intelligence. I mean, it depends on how you define it, but artificial intelligence is not just a science. It's an engineering discipline, and it's really not more of one or the other. It's part and parcel. Like they say at the beginning of the book, we have to decide what AI is before we start. Do you decide or do you discover? Well, in AI, you do both. You have to do both. We don't really know how to investigate intelligence without building it, Vico style. I only know what I build. AI can handle what science can't. Is that true? That's what I'm thinking. That's what I thought when I put these things together, which is weird because I've never thought of AI as being outside of science or outside of engineering. But if it can handle things that science can't, it has to be. I don't know. I'm just talking. And obviously it's not about aliens. Like aliens are like a good intellectual test. I don't know if there's anything to it, but it's an intellectual test. Like can your way of thinking handle even if there are adversarial agents in your environment about which you have, the 95% of information that's easy to get, not the 5% that's expensive. You got to go back and listen to a few retraces to know what I'm talking about here. But and I'll put them in the notes, but this is what we're talking about. So anyway, if you weren't convinced yet that we were headed in the right direction, I mean, it doesn't have to, I got to get off this aliens thing. People are going to think like, oh, I thought, no, but like the Major Murphy problem is what's interesting. When your adversary is an intelligent agent, and we're all in this situation all the time. I mean, it's usually not, it's nothing dramatic. It's like you're in elementary school and somebody's picking on you, or you're picking on someone and then they get you somebody, they get the best of you. You're at work and there's just this one person, there's always that one person, right? And they're not just like unpleasant. They're like, they're out to get me. Or maybe you're that person and you enjoy being out to get people, but those people don't want to be got by you. You're an adversary. You're adversaries, all of you people, school-age children, colleagues, military types, intelligence types. All of your adversaries are intelligent agents. Which means you have to learn some artificial intelligence. Chapter 4 will get you started. Although you'll probably want some momentum going into chapter 4. All right, that's it. This has been Retraice 106. Same time tomorrow, 10 p.m. Eastern. Retraice.com, retraic.com. Go to the website. It's cool. That's it. Signing off.